So, good evening, everyone. So, so we welcome Dr. Ayan Mitra at today's Cheenta Mathematical Science Seminar. So, Dr. Mitra is a pipeline scientist at the Vera C. Rubin Observatory Legacy Survey of Space and Time (LSS). So, it's one of the largest and the most advanced optical telescope projects set to operate in Chile. So, he's actually based in National Center for Supercomputing Applications in Urbana-Champaign, Illinois. So his research is mainly focused on dark energy and supernovas. So we look forward to your talk. Over to you now.
Thank you for inviting me. Let me share my screen. So, like the title was advertised, I don't know how much of you are people over here familiar with different terms over here: cosmology, supernova 1A, LSST. They're all individual keywords, jargons. I will go through them over this talk and try to give an overview of what I'm doing and what the bigger goal of this whole bunch of people working in the collaboration of LSST is. So the photo actually that you see in this title's slide over here is actually a real time-lapse, like a animation, not animation, video of the Rubin Observatory actually in the Chilean Atacama deserts. So at the moment it's in it's almost working, but it's not taking real data, stage data, but it's already taking data, but it's like testing phase going on. So do you see there's a time lapse of how it's at the night sky, or the dome is moving, taking photos, and on the background you see this beautiful night sky. We'll come to it in a moment. So before I go into the LSST and the technicalities, I'll take a step back and just give a bit of a theory recap what this all means. So most of us are very well familiar with stars, planets. I mean, you don't need to know the full complexity of it, but you're still like the night sky, you look up, you know the basics. Now, broadly, what, like the title showed, we're interested in here is supernova 1A. So where it's a part of a life cycle of a star, and so every star, they can go either one way to become like a massive giant red supergiant, or they can, a few of them don't go that way and become an average red giant, typically from average stars like our sun. And this evolution whole cycle, like the star, a red giant, then at some point it becomes a nebula. All of them are individual states which are specialized, and people are specialized in their life to study those stages. Like it's a very detailed study based subject itself, all of those individual stages. Now, if you see to the right of the slide, when it reaches planetary nebula, and then at some point it becomes something called as a very small dense thing called white dwarf. If it reaches a white dwarf, then at some point from there, it kind of, there's a fight going on between how much further small it will get or how much it will go bigger. There's a outward and inward fight. At some point it reaches some threshold, bursts out. When it bursts out, it gives what is called as a supernova 1A. There's a wonderful animation from NASA which shows how type 1s are actually formed. So supernova have various different categories: supernova core collapse and supernova under core collapse. There are many subcategories, and then there's supernova 1A. We're interested in 1A, and here's a animation. Basically, you have a white dwarf accreting matter, so it's a binary system, like or whatever is near it, it starts pulling, and then it reaches a limit named after the great Chandrasekhar, and then it cannot sustain itself anymore, it bursts out, like you see. A very interesting fact is, when this bursting happens and supernova is born, the brightness is so bright that it outshines its entire host galaxy. So if you don't know the distinction between a galaxy and a star, I'll still give a very so millions and millions and millions of stars and many other things comprise to make one galaxy. So if you can imagine, like if a football is a star, the football ground is a galaxy. Now imagine I'm saying that one of those star or football bursts out and forms a supernova. At the moment of bursting, it becomes so bright that it is brighter than the entire football stadium. That's how bright a supernova 1A becomes at its time of birth. So it's a very special cosmic event. So further back, if we go back a bit more, we'll come back to supernova a bit more. Let's have a bigger look at the perspective of the universe. Now, for last 100 years, or since the dawn of modern physics, right, like 1900 sometime, it's been very well approved and agreed upon by cosmologists, astrophysicists from all different backgrounds, that whatever study they have done, they have come to this agreement that the universe is homogeneous and isotropic. What that means is that we are here on the earth somewhere, placed in somewhere in the universe, and we don't possess, that place is not a special place. Like probably you have heard in the Middle Ages that, or in some religious texts, that we are at the center of the universe, blah, blah. No. We are just as equal as any other part on the space-time distribution of the universe. That means homogeneous and isotropic, meaning there is no directional preferential directionality in any side of the universe. Wherever you go, wherever you stand, if you take a statistically random sum objects from there, and if you take that like that in many other places across the universe, and if you do a statistical distribution, you will find more or less they are all equally distributed. So there is no speciality in any direction. I'm talking about this on big scales of the universe, not like in very small, like zoom in. No, zoom out, and if you see, it looks like that, equally distributed. This has a very profound significance, the understanding that the universe is homogeneous and isotropic. If we think, and that is what we understand, our data matches base, that the universe is actually homogeneous and isotropic. Now, that gives us a lot of leverage to measure and understand the mechanism of the universe. So when we see the night sky, now cut all those crap out. Now think you have a telescope pointing at the night sky, whichever telescope. Maybe you have a small telescope in your balcony and you are looking at the sky. The only thing, as we human beings standing here on the earth looking in the night sky, the only thing we can get from us to the Hubble Space Telescope is some electromagnetic waves, like light. Mostly we're telling about light waves, right? Photons coming and hitting your telescope. Maybe there's a receptor, there's a camera, something, just like how a camera works, right? And it records that in the flux of photons sitting in. That is the only raw thing that you are getting from the universe as your signature, from which you can get information. What that thing is basically, in the words of science, is, so we're pointing at the night sky, we're seeing a bright luminous object, whatever object that may be, planets, stars, nebula, supernova, whatever. Now that is a luminous source, right? And that luminous source is just throwing out fluxes or light waves in all directions, 360 degrees. What we record is a part of that. That's what called the flux, meaning basically it's the luminosity over the 4 pi r square. R square is the radius, so it's just basically the fraction of the total light that we receive in our telescope. That, what you see over here, is the F. Flux is equal to the luminosity by 4 pi dl square. That dl is the r, meaning the radial distance from us to the object of whose light we're receiving. Now the amazing thing is, because the universe is homogeneous and isotropic, we can use something called as a scale factor. It's very much like a time unit or distance unit, but it is not a distance unit. But it analogous, it's easier to understand that way. For example, if I give you an example, let's say You are in somewhere in Kolkata, maybe from Salt Lake to airport you need to go, and you think, okay, I'll take the VIP. It's like 10 kilometers road plus minus. What you are actually saying is 10 times 1 kilometer, right? So it's the standard unit. The 1 kilometer we're talking about here, let's call it scale factor of the universe. And this is entirely possible because we're thinking the universe is homogeneous and isotropic, meaning whichever side we look at, it is uniform, and I can use a scale to measure the distance as a factor of that. Because of that, now, whatever you are measuring on your telescope, you're measuring some object emitting some light at some wavelength, but you have to understand that the universe is big, very big, right? Beyond our understanding, very big. And the point when they emit it to the point when it reaches our telescope, in between its flight, the universe has expanded. So the wavelength has also moved. It's kind of like the Doppler effect that you know in sound, in train. If you are not aware, I'm assuming you know what the Doppler effect is. So knowing the wavelength of the emission at the point of emission, like the wavelength, and knowing the wavelength at the point of receiving at our telescope, if we take the fraction, we can directly relate it to the scale factor of the universe. It's like the scale of the size of the universe, like how much it has expanded. And again, not going too much into the mathematics of this gives a term called redshift. This is a cornerstone of modern modern astronomy. Anyway, so taking all of those, if you take the flux, coming back to the flux relation, so you get the flux of an object on your telescope. Now the beauty is every object gives a different luminosity, right? But some objects, if imagine they always emitted a constant luminosity. For comparison, you have a bulb or a tube light in your room, right? That bulb or tube light, always throws its energy at a constant level. It doesn't fluctuate, right? That is what I'm calling as a constant luminosity, as opposed to, let's say, a fire on a coal burning on a ground. So it goes up and down based on wind, how much coal is there, what's the temperature, etc. No, it's a constant luminosity source. So if such an object is there, then this formula, flux is equal to luminosity by 4 pi dl square, is even more interesting. Why? Because, okay, now let's say you have a telescope, you point to the sky, and you know an object you want to observe, you point to that, you are observing tonight. It has a fixed luminosity, it is traversing some radial distance across the universe, coming and hitting your telescope, you get a flux. You go back tomorrow again, maybe in 1 month time again, maybe in few years time again, point to that same object, if it is there on the night sky, and you measure the flux again. So you'd have a recording of different nights of flux of that same object in the night sky. Now, like I said, if it is like the bulb or the tube light, if it has the same luminosity, then you can just take the ratio of your flux measurements of the different days, and because of L is constant, it gets cut out, and your left flux ratio is equal to the ratio of the distances, that the denominator luminosity distance, meaning the distance from you to the object. If you look at it once more, it is again profoundly interesting from such a simple mathematical relation. What this is telling us, like if the source you are observing has a constant luminosity, if you measure it at different epochs of time, and if you take the ratio, you can get an understanding of the distance of that object is from you on the universe, wherever they are. Maybe they're on the other side of the universe, but you get a ratio of the distances. So imagine if in between your nights of observation, the universe has expanded or shrunk, that will be reflected in that ratio of the distance. So you can get a idea of how fast the universe is expanding or not expanding or deaccelerating, just by measuring the flux and a very simple mathematical relation, right? So, like I said, measuring fluxes at different cosmic times, we can get a scaled distance estimate of the universe. This is huge, like profound. But then you can ask, well, we can point to the sky and we can observe anything. And why are we talking about only supernova 1A in that sense? Many things, right? Like galaxies, blah blah blah. True, but supernova 1A also has some additional like significance which makes it stand out from the rest of its peers. The main standing out factor is like, one, they're very bright, like I mentioned, so they're very easy to see even from very far distance of the universe. They have a very clear signature. That's a type 1A supernova. Their distribution is such that they're very unique distribution, which is uh, very easy to recognize. So in comparison, if you're observing galaxies or something, there are different millions of types of subtypes of galaxies. So there's a lot of work to take, understand which galaxy it is, blah blah blah, and then you conclude inference what their characteristics. But the supernova distribution is very unique and easy to detect. And then there's this one thing called standard candle. This is a phenomena that makes it like way above its peers, which is what you see on the right. There's an animation going on. It's a brightness distribution as a function of time. The x-axis is the days, which is time. The y-axis is its brightness distribution. Meaning, as you detect a supernova, or you think it's going to happen, so you start observing, you take note of your brightness, you plot it, you see it gets brighter, so your y-axis value increases and then it falls off. After it bursts, some day stays bright and then again it wanes off. There are some, depending on the size of the host galaxy or the supernova, etc., there are some additional corrections we need to do to make it a standardized supernova, meaning apple to apple comparison. So all supernova can be compared between each other. Those are called like color corrections, stretch corrections, meaning that the brighter supernova is a bit emitting more on the bluer side of the electromagnetic spectrum, or a brighter supernova lasts a bit long on the night sky than the dimmer supernova. If we correct for those minor things, and then we again draw the light curves of each of the supernova, we see, like as you see in this animation, there are different, they have similar patterns, but they vary on the y-axis. But if we correct and we redraw them, they all lie on a single template, very like uniformly, almost like only 10% variability. So they have very standardized homogeneous objects. Hence we're calling them as standard candles, meaning we can use them as a ruler, as a measuring tape, to measure them, using them to measure the size or the speed which the universe is expanding. Why? Because let's take an analogy. If you're standing in the night at a road, like some big road, and you see a car coming from distance, right, with the headlights on, without knowing anything, your brain automatically processes to tell you, right, like how far the car is and how fast it is approaching you. You don't need to do all the fancy mathematics, which is actually happening real time. Just by understanding the size of the light and how fast it is getting brighter or dimmer from you, you already know that the car is coming to you very fast or very slow, and like how much time it will take to be near you. The mathematics that's happening behind this is basically, again, it's the same thing. The headlight of a car, your brain knows, has a fixed luminosity, and therefore it maps out the dimming or the brightening of that, and how much it's like taking individual snapshots frozen in time very quickly, and it's doing an interpolation and it telling, okay, this is the speed it is coming towards me or not coming towards me. Exact same simple analogy or idea is translated in this space using supernova. You see a supernova at somewhere in the night sky, you see tomorrow again, you see a few days after again, and you try to understand how much it has got dimmer with respect to the first night or brighter, and then you measure this, how much has it gone away or closer to me. Hence we call it a standard candle. It's again an amazing tool, very simple logic, but a very robust mechanism that can help us to understand the size and the speed of the expansion of the universe. Here's a bit more technical slide. So basically what we see over here, like you see on the left, this is in red, it's written distance modulus. So basically distance, imagine in your mind. So the one equation on top you see is mu equal to mb plus capital M naught. So M naught, the big one, is basically your absolute magnitude, meaning we're doing a standardization. So if your supernova were like at a fixed distance from you, which we use like 10 parsecs from us, what would be the luminosity? Because what would be the distance or flux brightness? Because all this is possible because we know the luminosity of type 1 supernova is constant, we know that at a given distance it will always have the same brightness. So we fix like the like putting a fixation on your equation. That's your baseline. Now we're saying with respect to that, this is the small term mb. With respect to that, how much farther the supernova in the real night observation is, and then we compare and put an apparent magnitude, which is mb. Adding those or subtracting between those gives you the distance, which is we call distance modulus. That is how simple it is. So you measure the brightness of a supernova because it has a fixed luminosity, and after some corrections you can use it as a standard candle. You measure it at different times of its lifetime. You can translate that to a distance estimate, how far the supernova is, with some additional complexities, of course, going inside that. I'm not going into that. The equation on the bottom that you show, the bigger one, is actually those additional complexities put in. Like you remember the standardization thing, color correction, stretch correction, meaning the light curve is bluer or wider, blah, blah, blah. But the broad theory is this: if you measure the brightness, and if you know the base brightness, like the standard one at a given distance, you add or subtract, you get a distance. This is amazing. How does now that translate to our cosmology, and how does that help us in understanding the cosmology? So Einstein, in the last century, at some point, he wanted to, of all the various things he was interested, he was also interested in cosmology. And with his theory of gravity, which you all know, and then the general theory, etc., etc., at some point in his life, he was working on modeling the universe with equations. So there's the famous Einstein equation, G mu nu is equal to 8 pi G T mu nu. Again, this is a separate topic itself. I'll not go into it. People are specialized all their life to work on that. But the main takeaway was that Einstein was trying, he had believed so strong enough to think that the universe was static. So he was trying to fit his equation to solve, agreed on the isotropic and homogeneity of the universe, but he was also assuming there's a staticness of the universe, and so he was trying to fit a static model. Now, just the G mu nu is equal to 8 pi G T mu nu, the Einstein equation was sufficient. So to force it to become a static solution, he added an additional term in that, which was called lambda, and would be famously go on to be called as the cosmological constant. Now with the cosmological constant, you could throw in like a constant in, if you solve a integration equation and you add a constant to solve whatever purpose you need, is lambda was like that. So you could now do a static model also. What happened later was that about the same time, there was this famous person called Edwin Hubble. I'm pretty sure many of you have heard of him. Hubble was an astronomer, and he was observing the night sky real time, instead of, unlike Einstein, who all his life sat in a lab and was doing theory. But Hubble was an observer, and he was sitting on a telescope every night, and he was looking at the night sky, taking data and making a chart of that. And then he plotted, and what he plotted was not agreeing with what Einstein's equation, including a cosmological constant static equation, was. So Hubble and Einstein had interactions, and then Hubble said that what my data shows, and this is real data, is in complete disagreement to what your static universe is. Einstein would later go on to tell famously that adding a cosmological constant to the Einstein equation was the biggest blunder of his life. And what Hubble plotted that night, or during that period of his research, was basically the distance versus the velocity at which any object that he sees moving away from us, receding from us. That plot till date is one of the cornerstones in modern cosmology, and they're famously called as the Hubble diagram. and the and so also Lemaitre in France was doing the same thing, and he had similar understandings. He came to the same conclusion. So basically, they had a very simple equation derived from their data when they plot. This is the original plot you see over here. V is equal to H naught d, where V is the velocity of recession of an object from us when they observe it multiple times over a period of time, and the distance is the distance of that object from us. So it's moving away, and V is the velocity with which it is moving away. The constant in added there is the H naught, and that constant is still today one of the cornerstones in modern cosmology and astronomy. It's called the Hubble constant, and the study of Hubble constant, it's a precise measurement, is very much the center stage attention of even modern science. It is paramount. Anyway, so then came the Hubble diagram, Hubble constant, etc. And then people were mostly agreed that the universe is expanding, not a static universe. Cut to modern times, when our electronics became stronger, our cameras were stronger. You probably know of the famous Hubble Space Telescope, which is still in action. All of them go into space, and then we start observing the night sky. Imagine this once more and try to digest the significance of it. In the entire lifetime of human civilization, I don't know how long the civilization is, hundreds and hundreds of thousands and thousands of years. In the entire timeline of human civilization, this is the first time, like 20 or 30 or 40 years back, that we are able to send a telescope in the night sky outside the Earth, like in the sky, and observe deep into the universe, first of its kind. And so we have unprecedented view of the depth of the universe. First time again, everything is first time now, and we get to see real universe through our own eyes, without any assumption, any pen and paper stuff. This is real data. And what we saw was made the astronomers awestruck and surprised, and it fails movies. What they saw was that the observations, so there were some of astronomers, many were observing many different things, but some were also observing type 1 supernova. And when they observe it at different periods of or nights of the years and months, they observe exactly what I've been telling you, that the distances of the supernova from us over a period of time are getting bigger, meaning they're going away from us. Not only that, they're going away from us at a speed which is accelerating. So imagine tonight, just for an example, imagine you see the supernova tonight at, let's say, 10 kilometers from you. Tomorrow you see it at 50 kilometers. Few days back after, you see at 1000 kilometers. Why is it surprising? Because we already have a theory of gravitation with a cosmological constant, or not a cosmological constant, but kind of expanding with the Hubble law. And our observation should match with that theory. The theory says, as till up to this observation, the theory said that you have a universe which is expanding. Since Big Bang, it is expanding, not a static universe, but it's expanding. But it's also expanding following the laws of classical mechanics, meaning there's friction. So it cannot indefinitely go on speeding up. It gets a highest point, and then because of friction from the other gravitational bodies which are getting bigger, like the planets and the clusters and etc., they're pulling each other, so there's a friction, so it will slow down. Exactly like, imagine if you have on a dining table, you drop some drops of water on the tabletop. It initially flows out, and then it comes to a stop at some point. Before coming to a stop, it slows down. The idea we were expecting to see was that slowing down phase, because we thought the universe is still expanding now, but it's slowly expanding. But what the observation was in the 90s from the Hubble Space Telescope and other telescopes, that it is not slowing down. It is in fact accelerating. And every other night we observe the supernova from the previous night or the previous time, whatever the duration be months, days, weeks, years, it is getting faster and faster. This is a revelation that got the full community like crazy. Well, what's going on? What goes on? So at some point, people had to confess and face the truth. So either your Einstein's theory of gravity is wrong, or there is something in addition to the existing theory that we are missing out, some blocks which needs to be accounted for to address this expanding and accelerating universe. In comes what we call, so at this point now the cosmological constant makes a comeback, a huge big comeback in a different avatar. It comes back now to fit in the purpose of this accelerating universe. Now people add this term, revives it, and says, okay, maybe the cosmological constant is now relevant again in a different way. Maybe this is the one that we can use to address the acceleration of the modern universe. So one thing was clear, the data is showing that the universe is accelerating. Everyone accepted. There is no denying that fact. What is not clear is what is the theory happening underneath it. That's what we're discussing now. This was such a big revelation in the entire lifetime of human history, that the Nobel Prize in Physics in 2011 was given to these people, Perlmutter, Rees, and Brian Schmidt, for the discovery of the accelerated universe using type 1 supernova standard candles. Now, remember I mentioned Hubble diagram. The Hubble diagram is still very much a hot topic in modern times. So basically, you take your different events of supernova, you plot them on your x-axis or the redshift. So redshift kind of gives you an idea of the distances and the velocity. There's more theory to it. I'm not going to it. And the y-axis is basically mu, which is your distance modular. So your velocity and distance is still scaled using the Hubble diagram. What we see here, each of those points is a single supernova plotted on this redshift axis. There are about 100 events. This is still an old plot. It's like maybe 10 years back, 2010, 12, 13 plot. And with that, now remember what we're discussing, what is missing. We need to add something to the theory. What is the clog in the wheel that is missing to address this accelerated universe? In comes the cosmological constant, like I mentioned. The cosmological constant is basically used to address what is called dark energy. Why is it dark? Is it dark because of two reasons? One, it's not visible with our optical telescopes, because of course if there was, then we would have already known by now there's something in the universe. So it's not visible, hence it's dark energy. The other thing, why is it dark? Mainly because of this, it's not visible. Now the dark energy is actually to if we do a back calculation to fit it in our existing theory and see how much of dark energy is needed to address the current time's acceleration, we actually see that it is the dominant source of existing component of our universe's materials. 75%, about 3/4 of the component of what the universe is made up of is assumed or expected to be dark energy. Remaining 21% is what we call dark matter. It's dark matter. I mean, people often say dark energy, dark matter together, but they're very different in purposes. Only this remaining 4%, 5% thing is what we call baryonic matter, which is basically the visible universe that we see. You, me, the table, the car, the aeroplane, everything that lies within that 5%. And this dark energy, like I highlight over here, is a fluid with a negative pressure. So the negative pressure is kind of gives you a negative, like instead of opposing the deacceleration, which is supposed to slow down the expansion, it gives a negative pressure. So it kind of gives you the acceleration in the modern times. And that kind of helps us to modify the general relativity, general theory, or maybe change it. There are alternate study bands in modern physics, astronomy, where people studying alternate theories to completely give away relativity, theory of general relativity and gravity, and maybe something new, like modified gravity, which could address this. Anyway, that's a separate topic. But this is mostly the standard cosmological model with dark energy as the helm of it. Um, Very funny thing, I don't know if I have time, but people across, I have met many people who are not from this background, and they have different approaches and take on this topic when I say dark energy. Maybe after the talk, if we have time, I will share some of those funny anecdotes. Anyway, so what is the dark energy? What does it do? So dark energy smoothly fills the space. It's very uniform but unseen to the naked eye. It dominates the universe today, and that's why this acceleration. The word today is important. It was not like this forever in the past. So like you see over here, today the dark energy is the dominant source, 75%, but 13.7 billion years ago, which is the time we think when Big Bang happened, it was non-existent. So there's an evolution that has happened. At that point in the past, something else was more dominant. Matter was dominant, radiation was dominant, etc., etc. But because the dark energy is dominant in the modern time, so it is pushing this acceleration. And the acceleration of the universe is also a modern time. So we're living in a special time, epoch of the universe's history when this is happening. The acceleration was not happening forever. It's happening in the current epoch. So it's a circle which brings us back to the stone man age. The stone man saw the night sky, he knew nothing, and he was like, where did it all come from? Now we are sitting in the most fancy laboratories, we still don't know anything. We have so many questions. Now, why now? What is the vacuum energy? What is the nature of dark energy from? What is happening? We have no answer to most of them. We're doing a lot of science. We have some idea, but there's no conclusively I can tell you this is it. No, we don't know. Here is some of those mathematically interested terms of dark energy. It derives its base from very much like classical thermodynamics. So if you have done thermodynamics, or if you do, you will know there's a very typical is doing an equation of state, etc. So dark energy theory is based on that, which is understandable because the basics of thermodynamics is vital in explaining the understand of the mechanism of the universe. All that put together at the moment, this is what we think is our best guess of how the map of the universe looks like. So let's try to understand a bit before we finish this chapter. So the x-axis, or from left to right of your screen, what you see is the evolution of the universe. And as you see on the bottom of the screen, it says Big Bang expansion 13.77 billion years. That is what we think as the lifetime of the universe from Big Bang. So on the left edge, if you see, there's the quantum fluctuation, inflation, blah, blah. That is the point when Big Bang happened, the very Big Bang, the big light. Then at some point, there's the light that happened. So in some analogy, it's similar to if you have read the Bible. They say like there was darkness, and then one day God said, let there be light, and there was light. It's something like that. So there was light. There was not light from Big Bang. There was a 10 minus 43 second gap, and then cosmic microwave background happened, and then the universe became clear, like transparent, and the light emerged. All the way to the right is the evolution happening over this 13.77 billions of years. There's structure formation happening, galaxies getting bigger, then clusters, all of those, happening towards as you move towards the right, which is progression in time. And one thing I want you to notice is if you see towards the right edge of this universe's map, you will see there's cusps towards the bottom and the end of it. It's like a flower vase going out. That is what is signifying the acceleration in the modern time. So the universe's spatial dimension or the size has suddenly popped out than what it would have been throughout if the natural extrapolation happened from the initial times. So there was this this additional popping out is because of the accelerated expansion that is happening at the current epochs. Again, the question is central to it is what is driving it? No ordinary general theory of relativity can explain this. Dark energy, our best guess at the moment is dark energy. How to model it is what is the hot topic of last 20 years of current cosmology. How is dark energy characterized? And I also work on that. I work on modeling it using supernova 1. There are other probes also which you can use. So that's a initial primer. I will now very quickly, maybe another 10 minutes or so, go through LSST and what I'm doing at the moment. So again, so there is a lot of telescopes, a lot of government fundings have happened once they started to see the actual results on the ground. So in last 20 years we have had iteratively built more stronger and stronger telescopes, both on ground and on space. And you probably heard the name of a lot of those, starting from Hubble Space Telescopes to the current ones like you probably heard JWST, Roman. Right in the same league is LSST. And they cannot be built by a single few people. They're huge. That's like it's a project as big as anything you can think of. It takes governments, different countries, collaborations, people from different backgrounds, like not only physics, not only astronomy. It's like engineers, computer scientists, mathematicians, statisticians. Everything is needed to make such huge projects a success. And so, like I was mentioned, supernova 1 is not the only way. There are many other ways you can map, and they have their individual specialities of what you can gather up information about the universe. There's like galaxy clustering, CMB, if you probably heard of that name, cosmic microwave background, gravitational lensing, etc., etc. And they have all different things they measure. I'm mostly working on supernova, so it measures that distance, as I mentioned you, using a standard candle theory. So LSST, a bit of about the LSST. LSST is one of these, it's a Vera C. Rubin observatory named after Vera Rubin. It's a flagship project of US Department of Energy. A fun fact, in spite of all the budget cuts and etc. that you might have heard on the news, somehow the LSST did not get a cut because it was overwhelmingly so impressive that even people in Congress found it hard to put down. It is right at the compare its competitors at the space telescope like JWST and Roman. We will use all of this like supernova, gravitational lensing, clustering, different things to probe the universe. It's set up in Chile, the Atacama deserts, southern. So Chile is southern hemisphere, so it will observe the southern sky. Apart from the physics of it, which is a state of the art, its camera is a state of the art, meaning it is the digital camera that you have on your phone or etc. It has like we talk about few tens of pixels, like 20 pixel or 30 pixel camera. The LSST will have 3.2 gigapixel. That is the biggest digital camera ever built till date on Earth, built by I think Carl Zeiss, and the lens is also built by Carl Zeiss, which is an 8.4 meter class mirror, the lens. The telescope dome is huge, 35 ton floors of building. Apart from the astronomy and the optical marvel that it has, the computational facility is also state of the art, meaning it has huge, it will record like petascales of data every night. Or not in every night, I think some thousands of terabytes of data every night. So there's a dedicated computers group which has like some of the best brains in the world working on that. This is a cross-sectional view of how it looks. I'll move through them quickly. It's a huge structure. It's a challenge to. It was built in California and it was taken all the way straight into the deserts by a 747 Boeing because it was so big. Just a fun fact over here. So it's very big, like a giant, but it is very fast of its feet to move on this across the sky. So it does a full sky in 18 seconds. So it will scan the full sky, and it will do all throughout the night during its lifetime of operations, 1,000 times every night. That's quite a thing, and do it for 10 years. So we will have humongous amount of data. It's like we're very overjoyed about that. How it works is like, so it's in Chile, so base site as you see on the bottom of the map. But the operational centers, data centers are in East Coast US, West Coast US, California, and in at NCSA and in New York. And then we also have a European counterpart in France where they have direct and data. So it's huge data gathering capacity. LSST, like I mentioned, will observe different kinds of things in the sky, not only supernova and dark energy. And so there are different individual groups, like it says. So like probably you understand if you're a bit familiar with astrophysical names, they are self-explanatory. Like there's AGN, active galactic nuclei, so AGN group. Then there's the TVS, and then there's the Milky Way, which is SMWL, etc., etc. And then there's the desk, which is, I read, marked it, which is like dark energy science collaboration. So I work in desk. And here's their footprint. Interesting to know, we have our footprint partners in India also. So people in IUCA in TIF has membership to work in desk, and they're quite vibrant. Here's a collaboration photo from last 2024 in Geneva. Okay, so what you see over here is the night sky, that is a full sky basically. This is not the sky that you see over here typically, but imagine this is the full universe's sky. And the one on the red is the southern sky, meaning the southern hemisphere. On the brown on or gray on the top is the northern sky. And you see, if you see, there's a semicircular arc going throughout the map. That's the footprint of the Milky Way, our own galaxy. The LSST will observe that the green patch that you see, and if you can see, I don't know, there are some 4 small dots, those individual points also. The difference is the green big patch, it's a very wide, shallow survey. Shallow meaning it will not go very deep, but it will just superficially, but very quickly, and do a lot of surveys of that. So whatever on the surface you see. The smaller dots are the pencil beam surveys, meaning it will focus on a small area and it will give a lot of energy into it, so it will measure very deep into that sky to go very back in history. And there's all these facts like millions and billions of stars, alerts. Okay, there's 20 TB of data every night, etc. I'm not going into that. Current status is it is already operations, but it is early operations. Science ready operation will start sometime in the summer this year, and then by next year we'll have a first year's data release. I want to, before I come to my results, I will take one more additional interesting thing. So in the lifetime of supernova study in modern cosmology, when I say modern, means let's say last 50 years or 60 years, supernova, when detected, they can be detected using, so you have a telescope, you measure. If you know how a telescope works, it has different filters. So you can put different filters to measure the wavelength of only that specific filter, cutting out everything else, meaning it will only allow a certain wavelength to pass through that filter. This is important because some filters have some additional advantages over some other wavelength filters. So the way of measuring those, if you have done experiments in colleges or have heard about it in high school, you can do either spectroscopically. So imagine the spectrometer if you have in your darkroom labs. So you can do that and split it up and measure the individual wavelengths and get an idea. Or you can do what is called using a photometry. So you have templates, etc., and measure that. There's a trade-off between those two. If you do a spectroscopically measurement of the supernova, it's very accurate. You get the accurate redshift. If you get the redshift, you can get the accurate distance measurement. But doing a spectroscopic measurement is also very expensive, and you need to have a lot of telescope time. So it's not always feasible. If you have a lot of objects, if you have only 1 or 2 objects, you can do that. But like LSST is so big, it will observe thousands of supernova. You cannot follow for all of them. So the trade-off is then you do a photometry. A photometry is a more kind of like a statistical measurement. So you can do a lot of those at a quick time. But the cost you pay is that the quality. You will have some error in your redshift measurement. And so your distance estimate might have some error also. So you will not get an accurate measurement. But with the huge number of objects, we have to use photometry for a lot of them, because otherwise we have to throw them away. So what's the point? Why I'm saying all this is because in the history of supernova measurements in last 50 years, initially there were very few supernova, 10, 20, 50, 70. For example, the supernova sample that won the Nobel Prize that were used for study had only 50 something supernovas. So you could cherry pick them, study them thoroughly using spectrometer. So you can point to telescopes and point to them. Most of the last 20 years, when people do supernova survey, they are talking about spectroscopically classified, meaning the type 1A or non-1A. First you classify them, and then when you classify, you know it's a 1A, you follow them back to measure their redshift, because that gives you the distance. All of them was done spectroscopically. And now cut to the bottom row. Because now we have so many objects, we cannot do all of this. So we're doing a bit of photometry also. So we're throwing away, initially the thought is we're throwing away quality, but if you can do a fully photometric approach, like classifying photometrically and having redshift also photometrically and do cosmology with that, you will have tens and tens of thousands of supernova. Now, if you have done statistics or mathematics, you will know that you, in an error analysis, error typically given by sigma, scales as roughly proportional as 1 over n, n being the number of events. So if your n increases, the number of events increases, your sigma or the error shrinks. So more events is always welcome for us in the data. So we have a less number of error on error budget. So we are very keen. Whole community has been trying this for many years to do a fully photometric analysis to see if it's feasible. It's only in December that, and I'm very proud of that, that we and I led this project, that we kind of first of its kind in the history of modern cosmology, that we did a fully photometric approach of type 1 supernova cosmology in the LSST era. And it's still using a simulated data, but it kind of does the road work and prepares the ground for in a year's time, when the real data starts operating, that we can actually apply that theory to the pipeline with the real data and get cosmological results accurate for dark energy estimate, using not only spectroscopical sample but also photometric sample, all mixed together. So you take the full sample of thousands of supernova instead of few, and that gives you a better estimate of dark energy. A very approximate pipeline of a standard modern day supernova analysis looks like this. So you have some simulations, don't worry about that. Then you have a light curve feed. You remember from the early slides the standardization. So you have the light curve, that's the brightness distribution, we call it the light curve. So you feed a supernova data to the light curves. And now, because we're doing all the photometry, remember, so we have to do the classification of supernova 1A. But because it's photometrically classified, there's a margin of error. So you can sometimes misjudge a type 1 as a non-1A. So for that, we take the help of modern machine learning AI, and so we use a photometric classifier, which is trained on thousands and thousands of samples, and then it kind of tests on the real data to give an object if it's a 1A, non-1A. So use that. That's also state-of-the-art algorithm. And then you remember we take those type 1As only after the classifier. We do a Hubble diagram, and then with the Hubble diagram, meaning we already have the distance estimate, we can use that to do a cosmology, meaning dark energy estimations. I will not go into the details of those, another 5 minutes. So basically, this is how the distribution looks like as a function of redshift on the y-axis and how many objects you have. So the redshift per supernova is mostly from 0 to 1.4 in our case, and that is generally around 1 where it peaks off. So it's a mix of now spectroscopy and photometry. That's a big thing, that there's photometric candidates also present there. So if you see on the legend on top, the photometry adds so many more objects, 5,000 more supernova. It's only a simulation of realism based on what we expect from LSST, but that goes on to show if we could add those photometric events, then our sample size would be way bigger. And this is what a modern day, our Hubble diagram looks like at the moment from simulations, and what we expect it to look in a year or 2 years time when the Hubble actual data comes in, the LSST data. What you see here on the left is the distance, on the x-axis is the redshift. Those red points that you see are kind of the contaminations from non-1A, non-supernova 1A events. Those could be other types of supernova. But the beauty is that the classifier, which gives you a probability of output of an object being 1 or non-1A, kind of properly flags them out. Hence, you see those red ones symptomatically distributed at a place which is very easy to see that they are not 1As, because they lie uh, at a unique position which you can figure out there's a pattern to it. So the conclusion is, at the moment we stand at a very interesting time, and we see that using photometrically classified supernova, which is the first of its kind in modern supernova cosmology history, we can use those, meaning we can have a very big sample, and we can use those to get the distance estimate of the universe and then dark energy estimation, and hence the most precise measurement of this distance scale of the universe till date in the entire history of mankind. As I finish, I'll finish off with let's restart this one once more. I'll finish off with a Hubble diagram animation of famous Hubble diagram since the time of Edwin Hubble to the modern times. So this was Edwin Hubble in 1929, then in 1968. You see there are 20 objects. So this is the famous Nobel Prize Hubble diagram. Then we had in 2014 a much bigger sample. There's a famous JLA, Joint Light Curve Analysis. Then recently there was Pantheon, Dark Energy Science. These are all seminal works of Hubble diagram. But you see the size is getting bigger. And we expect something like this LSST in 2 years to have the biggest yet Hubble diagram, and so the distance estimation of the sky. I'm sorry for taking a bit longer, but I finish here and I'm happy to discuss more on questions.
Thank you, Dr. Mitra. So actually we have one question on the board, if we can see that. So let me just read that out for you. So one of the students asked that if supernova 1A is so bright, then why don't we see a bright flash of light in the sky after a while of the event, as light would take time to reach Earth? And
we do
even
see it. We do see it. We don't see it with our bare eye, but historical records are there. So in 1600s, so back in those days, you can imagine there was no industrial revolution, no pollution in the night sky. There's documented history. There's two, one in China and one I think in Europe, that they had fire rain in the sky, but the description was such that we're 100% sure that was this description of supernova being sighted in the night sky. You can, if you are very lucky, maybe it's hard in modern times because our sky is so polluted. It's hard to get that clarity of the sky. But with a telescope, not even the most strongest one, if you are lucky, you can get a neighbor supernova with a moderately well-built telescope. You don't need to work too hard. You can see the flash.
Hello, yes, sir. I'm an engineering student, so focusing on future optical data networks. So my mind with means the infrastructure required for LSST means they are handling huge data like 20 terabytes. So to transfer that from the desert to the in US, like it's a huge pipeline challenge. So like what is the means hardest bottleneck to overcome it, and means like do you compress the data like for the speed, because means do you have a noticeable drop in your machine learning accuracy?
Yeah, so I'll try to answer it as much as I am an expert to answer this, because it's mostly for engineers to say. But Chile, which automatically, because it's host, they're the first stopping point. So Chile has a local center, so it gets the data first, the local ones, and then from there. So I think a lot of the raw data hits their server first, the local one, maybe in Santiago, somewhere in Chile, they get that. And then there's under the ocean, cables. So it's dedicated cable. It's again a marvel of what money can do. So it's a dedicated cable all the way from Chile to America under the ocean only for this. It's not a shared pipeline. It's a only for this. There's a cable there. So I don't know if that can have data loss. And then from US to France or something, I also think that is, I'm pretty sure that's also under the ocean dedicated cable, meaning it's not shared with anyone else. So I have no idea if that can be sabotaged or how much loss is that. To the best of my understanding, I think at the moment, time is not a problem. I mean, if there's a delay in receiving, it doesn't matter. We're not in a, it's not a like a medical science that we need in real time. We can wait. But the problem is if there's a degradation of data over its time. I don't think so, but maybe we'll have to look up the engineering manuals and people to see if there is, but I think no.
Okay, then thank you, Dr. Mitra. So we can close the session over here.
Okay, thank you. Bye.